Yo kids, so as promised, here's the solutions to the home insulation unit of physics this week. I hope you managed to have a good go at it. If not, just watch and see if you agree with the stuff I do on it now, right? So question number one was nice and easy. Look at this thermal image of the house. Where is the heat escaping from? And of course, the red areas indicate where the most heat is. So we've got the roof, obviously, that part there. We've got these windows here. And on this particular diagram, the heat looks to be coming out of here, which is the front door, right? So that's an easy mark if you get that on a test. The next thing I asked you to do then was to represent this data here for this house, the heat loss coming out of this house as a percent on this pie chart here. So the first thing we needed to do was figure out mathematics, basically, right? So for the roof, we have 25% of heat loss coming through the roof. And I told you that because it's 360 degrees in a pie chart, to convert a percent into degrees for a pie chart, times it by 3.6. So 25 times 3.6 give us the 90 degrees. The walls was, I believe, 35%. And if I times 35 by the 3.6, that gives me 126 degrees. The floor was 15%, times that by 3.6 gives us 54 degrees. The door was also 15%, times that by 3.6 gives us 54 degrees. And the windows was 10%, times that by 3.6, so you get 36. Now, it's worthwhile just checking that all of these add up to 360. They do, right? Now, I doubt many of you have a protractor lying around at home, so if you did have a go at this task, I imagine you estimated quite a bit. But it's going to look something like this, right? So for a pie chart, draw a line going straight up. 90 degrees for the first one, that's simple. That's just a right angle, which I'm sure most of you can do. So that was the roof. And don't forget now you have to put the protractor on the last line you drew, which is a common mistake that kids make when drawing a pie chart. So the next section for walls is 126 degrees. I'm going to put my protractor on the last line I drew. Zeros on the outside, use the outside numbers. 126 takes me to there. Line them up. Draw the line, don't forget to label it. So that's the walls. The floor was 54 degrees, so put it on the last line you drew. Zeros on the outside, use the outside numbers. 54 is there. Line them up to the dot. Draw it and label. That was the floor. The door was 54 degrees. Go back on the last line I drew. 54 takes me there. And if I've done it correct, by default, the last sector of the pie chart is now already done. The windows, let's just check. It's meant to be 36 degrees. Get the protractor, chuck it on the windows, line them up. Yep, and it's spot on 36 degrees. So happy with that, okay? So that was that exercise done. That's the type of thing you'd get on an exam, a numeracy based question. So consolidating your mathematical skills there. Right, the next task was to match up the items on the left: double glazing, cavity wall insulation, loft insulation, draft proofing curtains, and aluminium foil behind radiators, with the descriptors on the right. Okay, so let's do them in order. Basically, double glazing. So that's this one: gas, usually air or argon, an inert gas, right, for the chemists. Gas or a vacuum trapped within two panes of glass that acts as good insulators. So that's what double glazing is, right? Cavity wall insulation, I mentioned this in a previous video with the instructions for this task. In your house, your outer brick will have about a 4-inch gap, and then your inner brick. And in between that gap, they squirt like a foam, which acts as a really good insulator, which will keep your house warm in the winter and cool in the summer. Okay, so that lined up with that one there. Foam or fiberglass contain lots of air that is a good insulator, which means obviously it's a poor conductor of heat, keeping the house cool in summer and warm in winter. Right, loft insulation is actually exactly the same one. And this repeats itself down in that box there. Okay, so it's the same idea of foam or fiberglass being a good insulator. Draft proofing, you might have, if you go to your nan's house, you might see they have like a big snake thing that they put down by the kitchen door to stop the draft coming through, right? Just a really cheap way of stopping a draft, which obviously cools down the house. So that matched up with the bottom one. Draft proofing, cheap, effective, and reduce air transfer and therefore heat transfer between the outside and inside of the house. Curtains obviously cuts down the heat energy loss through the windows. And then finally, aluminium foil behind radiators. So we spoke about in 2 lessons ago when we did conduction, convection, radiation, we spoke about how shiny surfaces reflect heat. So an aluminium foil is a silvery shiny surface that will reflect the heat back into the room. So that's why they put them behind radiators, okay? So that's that task done there. Hope that didn't present any problems. Right, onto this insulation experiment task. Okay, so if you remember when we spoke about it, I have 6 different types of material: bubble wrap, wool, cardboard, fiberglass, foil, and 1 sheet of paper. I am placing them underneath a beaker of hot water, and underneath that, held in place by some cotton wool, I'm putting a thermometer. We're going to leave it there for 3 minutes, and we are going to see how good a conductor or how good an insulator each material is by looking at the thermometer reading. Obviously, the higher the reading on the thermometer, the better the conductor the material is. The lower the reading on the thermometer, the better the insulator the material is. So the first thing you had to do was work out the difference in temperature between the water in the beaker and the thermometer below the substance we're testing. Okay, so here's the results for that. We just had to subtract these numbers each time to get the temperature difference each time. Right, so I'm sure there was no problem with that at all because we went through it. Right, so here were the questions. Calculate the temperature difference. Right, we did that. Which material was the best insulator? Well, if we go back to the table of results, right, if you look at fiberglass, the thermometer only got up, so the room temperature was 20 degrees, and the thermometer only got up to 28 degrees. It only went up 8 degrees, okay? So that one is the best insulator. There was less heat being transferred from the hot water into the fiberglass. So fiberglass was the best insulator. Which material was the best conductor? Sorry, I didn't have that on the camera. There we go. Which material was the best conductor is the next question. And if you look at this, the 1 sheet of paper went up to 53 degrees. It had the smallest temperature difference between the water and the item itself. It went up 33 degrees from the room temperature of 20, so that was the best conductor, right? So that's the paper. Number 4, many types of insulation trap air, which is a poor conductor of heat. Which type of insulator works in a different way? So out of the ones in the experiment here, which one of these works in a different way to trap in air? And we just spoke about this 2 minutes ago with the radiators. It's the foil, okay? The foil is the one that works differently. And how does it work? Well, it's shiny, so it reflects heat, okay? So the foil is the different type of insulator. It's shiny and it reflects heat. Kelly argues that one result should be discarded because it is not a fair test. Which result should be ignored? I'm sure you've spotted it. Let's go back again. If you look at the cardboard, for some reason, the water temperature was 85 degrees. For everything else, it was 60, but for the cardboard, it was 85. So that one's got to be binned. Cardboard needs to be ignored because it was a different temperature. And then finally then, what variables do need to be controlled to be a fair test? Right, well, there's lots of them. I asked you to get at least 4, okay, but we need obviously the temperature of the water, right, the amount of water, the distance between the water beaker and the sample, the amount of time that you leave it before you take your readings, the thickness of the sample itself, etc., etc. Right? So I think there's about 6 things there. I was looking for about 4 of them to get the full marks, right? Brilliant. So that was our task done. I hope that went okay. So the last thing for this week's topic was this thing called payback time. And this is very popular on exams. It's quite mathematical, really. It's some easy mathematics to do, but we need to go through how to do it, okay? So the payback time, as it says here, is the amount of time it'll take for you to get a return on the amount of money you've spent on something. And to work it out, you get the cost of the product you've bought, and you divide it by the amount you save per year, annually, or per annum. So the payback time is always measured in years, right? And a very basic example here, if I paid £8 for draft excluders, and they saved me £4 a year, it would take me 2 years to make that money back, because 2 4s are 8. So the payback time for my draft excluders would be 2 years, right? Really, really simple stuff. So the payback time is how much you spent divided by how much you save per year. So question 1, if I spend £200 on loft insulation and it saved me £100 a year, what is the payback time? Well, I'm sure we'd all agree again, that's 2 years, okay? Because in 2 years' time I would have saved £200, which is what I spent on the loft insulation. If you spent £50 on foil to go behind radiators and you saved £10 per year, would it be worth buying if you intended to move in 3 years? Right, well after 3 years, because I'm saving £10 a year, after 3 years I would have saved £30. Well, I spent 50 quid on it. So really I've lost £20. So the answer is no, it would not be worth buying. If I was staying there for longer, of course it would be, but it does say I'm moving in 3 years. Right, let's complete the table then. So some basic maths. To get the payback time, you divide the cost by the saving. So 220 divided by 110 would take me 2 years to get that back. This time, if I spend £100 on floor insulation and it takes me 2 years to make my money back, how much saving must I have been making per year? So this time we need to divide these two things. So I would be saving £50 a year, and in 2 years' time I would have got my money back. I hope you see how that works. Over the page, £225 spent on loft insulation saves me £150 a year. If I divide those numbers, my payback time is 1.5 years, or 1 year and 6 months. Right, I saved £25 a year on draft exclusion, and in 1 year I got my money back. I got my payback. So I must have spent £25 in the first place buying it. And the last one, a more realistic one, if you spend £4,000 on double glazing, and every year you will save £125 on your energy bills, what is the payback time for that? So I'm going to do that number divided by that number, and it comes out as 32 years, a long time. Right, last question for this week then. Hope you're all getting full marks so far. The company sells thick and thin types of loft insulation, right? So let's write down thick there, draw a line, write down thin there, draw a line. Okay. The thick insulation costs you 300 quid and saves you £50 per year. The thin insulation costs £200 and saves you £40 a year, right? So that costs 300 quid, that costs 200 quid. How much money do you save after? Right, 2 years. So for the thick, after 2 years, I save £100. For the thin, after 2 years, I save £80. Okay. What about after 5 years? After 5 years, for the thick, I've saved £250. For the thin insulation, after 5 years, 540s are £200. So after 5 years, I've got my money back on the thin insulation. Haven't quite got it there on the thick. But after 10 years, on the thick, I've saved £500, which now puts me £200 in profit. I've paid back what I spent on it, and I've made £200. For the thin, I will have saved £400, and also that leaves me with a profit of £200. Question is, which would you buy? Explain your answer. Well, I'm going to say I would have bought the thin, because after 5 years I've paid it off. It would take me 6 years to pay off the thick. And even though after 10 years I've still made the same amount of profit for each type of material, odds are between 5 and 10 years I'd probably have to replace it anyway. Okay, so I would have gone with the thin insulation. And that's exactly the type of question you would get on your GCSE paper. So I hope you did well on that. It wasn't the most difficult topic in the world. We're going to look at density next. Okay, density of materials and calculating density, doing mass divided by volume, which you might have done in mathematics. And then it'll be time for another revision map and a unit test, right? And that'll probably take us up to half term. So I hope you're all well. I hope you understood that. And I'm going to say ta-ra and see you soon. Any comments, chuck them on Google Classroom for me, okay? All right, cheers, kids. Bye.